So in section 2.4, we're going to be going over measures of variation. So variation tells us how spread out the data is. And examples of this are going to be range, variance, and standard deviation. So I'll start with range, even though we've already did this, so I'll kind of go over it pretty quickly. So the range of a data set is just going to be the largest entry minus the smallest entry. So an advantage of this is that it's super easy to calculate. You just subtract two numbers and you're done, so it takes like 5 seconds. But the disadvantage for this is that it only uses 2 data entries from the whole data set. It uses the smallest entry and the largest entry. We know nothing about the middle entries, anything between the largest and the smallest entry. So just for a quick example, so calculate the range for this data set. So we need to find the largest value, which looks like it's 47, the smallest value, which looks like it is 37. So the range is just going to be the difference, 47 minus 37, which is 10. So this data set has a range of 10. Okay, so that's the range. Like I said, we already did it. So for variance and standard deviation, I'll go over the advantage and disadvantage before we actually get into the calculation. So the advantage for the variance and standard deviation is that it actually uses all of the data entries from the whole entire data set. And the disadvantage is that if we're doing it by hand, it takes not a very long time, a decently long time to actually calculate this. So before we get into the formula for those, we have to define what a deviation is. So a deviation for a data entry x is going to be the difference between x and the mean of the data set, mu. So the deviation is just the data entry minus the mean of the data set. So let's do an example using this data set. So I just wrote all of the data entries from smallest to greatest on the left, and then in the right column we're going to actually calculate the deviation. So the deviation is just going to be x minus the mean, so we obviously have to calculate the mean. So if we went through and calculated mu, we calculated the mean here. We add them all up, divide by how many there are, we would get 41.5. So calculating all these deviations, the first one is going to be 37 minus that mean, which is going to be negative 4.5. Next one is going to be 38 minus the mean, which is negative 3.5. And then it's 39 minus the mean, which gives us negative 2.5. And I'll just fill all the rest of these in real quick. We get negative 0.5, negative 0.5, negative 0.5, positive 0.5, 2.5, 3.5, and 5.5. So you can see that the deviation is negative. The deviation is negative if the data entry is smaller than the mean, and it's positive if it is greater than the mean. So those are the deviations. It just tells us how far away the data entry is from the mean. So if we're trying to figure out the spread of the data, we might think that it would make sense to actually take the average of all of these deviations and say on average, that's how far a data entry is away from the mean for that data set. The issue is when we try to take the mean or the average of these deviations, it's always going to give us 0. So that's because if we add it up, so I'm going to use the summation sign for adding. If we added up all of these deviations, we were always going to get 0. So if you don't believe me, you can go back up to this example and add all of those up. You're going to get 0. So trying to take the average would just always give us a 0. So the way that we actually get around this, we're gonna be squaring each deviation. So we're going to square each deviation. So we're going to raise it to the power of 2. That's going to make it positive, and then we're going to take the average of those values instead. Another way we can do this is actually taking the absolute value. But that's something different, so we won't worry about that just yet. So that actually brings us to the definition and the formula for the population variance. So for the population variance, we're going to denote this with a sigma squared. So this is going to be the Greek letter sigma, and it's denoted sigma squared, and I'll mention why it's sigma squared in a second. So it's going to be the sum of all of these deviations squared divided by how many there are. So first we have to find each deviation, and then we have to square it and then divide by how many there are, and that's going to give us the variance. So the issue here is that the units, since we squared the deviation, the units for variance are squared units. So let's say our data entries were lengths in inches or something. The variance would be inches squared. So that doesn't really help us. That's essentially meaningless. So in order to get back our same units, we're going to take the square root of the variance, and that's going to give us standard deviation. So the standard deviation is just the square root of the variance. So we always find standard deviation by finding the variance first and then just taking the square root of it. So it's going to look pretty much the same. It's going to be sigma equals the square root of the variance, which is the summation of the deviation squared divided by how many there are. Okay, so the whole reason why we do this and don't just use variance is because of the units. Standard deviation has the same units as our original data set. And since we're squaring it, since we're squaring those deviations, it's always going to be greater than or equal to 0. So we're never going to have a negative standard deviation. If we have a 0 standard deviation, that means all the data entries are equal. And in general, the more spread out the data, the larger the standard deviation is going to be. Okay, so standard deviation gets the notation with just sigma because it's more important, and variance gets sigma squared. So here are the steps. I'm not really going to be calculating this by hand too much, but I'll do one example here, maybe two, for calculating the variance and standard deviation by hand. So what we're going to do is we can set up a table. The table will be pretty helpful. We'll see why in a second. So for step 1, we're going to find the population mean, so find the average of the data set. Step 2, find the deviation for each entry, just like we did. Step 3, we're going to square each deviation. So using your calculator, you just square it. We're going to add those together. That'll be the sum of the squared deviations. Divide by n, which is the number of data entries. That'll be the variance. Take the square root of the variance. That'll be the standard deviation. So pretty messy, but still pretty doable. So let's do this example. So let's find the population variance and standard deviation for the data set, and let's round the mean to the nearest tenth. Okay, so step 1, let's find the mean. So this is actually our data set from before. We calculated the mean and said it was 41.5. So I'm just going to pause it real quick and fill in all of the data entries and deviations just because we already did it. And that's what we had for all the data entries listed out, and then all of the deviations for those data entries. So for the next step, the deviation squared. So we're just going to take each one of these deviations and square it. So negative 4.5 squared. So you're going to plug that in the calculator and say that's equal to 0.25. Or, whoops, just kidding. That one's equal to 20.25. I was looking at the wrong one there. And for the next one, for negative 3.5 squared. So type that in the calculator, negative 3.5 times negative 3.5, or use the squared button. We get 12.25. Negative 2.5 squared. We plug that in and we get 6.25. And I'll just list down the other ones real quick. And this is what we get for all of our squared deviations. So when you're plugging this in the calculator, you can actually leave out the negative sign. If you were including the negative sign, you need to make sure you have parentheses around the, like for example, negative 4.5. You need to have parentheses around it before you square it. Based on order of operations, the reason is because the calculator might make it negative then, your answer. These are always going to be positive. So a squared number is always positive, so just kind of be cautious for that. Okay, I'll actually make a note of that. So squared deviations are always positive. So to find the variance and standard deviation, we need to add up everything in this column. So what we're going to do is we're going to add up all of these deviations, these squared deviations. We're going to add up that whole column, and we're going to get 88.5. Okay, and then for the last part here, we want the population variance. The population variance, which we denote sigma squared, it's going to equal that 88.5 number, so the sum of all those squared deviations divided by how many data entries there are. So it's 88.5 divided by 10. There's 10 data entries here, which gives us 8.85. So that's the population variance. For the population standard deviation, so all we have to do now is take the square root of that. So the population standard deviation is sigma, which is the square root of 8.85, which is 2.97 about. I think I rounded here. So 2.97. So it's not awful. Once you make that little table, it's pretty simple. So that's the population standard deviation, 2.97, and the population variance, 8.85. So that was for population. The sample variance and sample standard deviation, you actually calculate it a little bit differently. So we use this one more often than not because realistically we're not going to have a population data set. We're only going to have a sample data set. So realistically we'd be using these ones instead. So for the sample variance, the formula is s squared. So once again, it's something squared for variance, except we use an s this time. So s squared is the sum of all of the deviations. So notice that I'm using an x bar instead of a mu because we're dealing with the sample mean instead of mu, the population mean. And the difference here is we're dividing by n minus 1. So the sample size is size n. We're dividing by 1 less than that, n minus 1. So the reason for this, which actually I've written down below here, this little note, it's for accuracy. We won't get into it too much, but just keep in mind that when we're using the sample stuff and calculating variance and sample standard deviation, we're dividing by n minus 1 rather than n. So the sample standard deviation is going to be, s. It is just going to be the square root of the variance once again. So it's going to be the square root of the summation of all of these squared deviations over n minus 1. So we're going to calculate it the same exact way, except divide by n minus 1 instead of n. So here are the steps. Same exact steps, like I just said. We're going to find the sample mean, which is just the average again. Find the deviation of each data entry, x minus the mean. Square each one of those deviations. Add them together to get the sum. Divide by n minus 1 will get us the variance. Take the square root of that to get us the standard deviation. So for this example here, what I'm actually going to do here is I'll pause it and I'll fill everything out and get an answer. So if you wanted to try it yourself, then go for it, just because we already did a long one and it's pretty much the same thing. Okay, so everything's filled in. There's the deviations. I calculated the mean, calculated the deviations. I squared all of the deviations. And for the last thing here, we're going to add them all up. So we're going to find the sum of all of these deviations squared. If we add up that right column, we get 43.88. And for the sample variance, we're going to take that number and divide it by n minus 1. So there are 8 data entries. So we're dividing by 8 minus 1, which means we are dividing by 7. And we'll get about 6.27 for our sample variance. So we do the same thing except divide by n minus 1 compared to the population variance and standard deviation. So now for the sample standard deviation, that's going to be S, which is going to be the square root of the variance, so the square root of 6.27, which is about 2.5-ish. Okay, rounded a little bit again. Okay, so if we were calculating the sample and population variance or standard deviation for the same exact data set, so if we ran through and divided by n, and then did it and divided by n minus 1, the sample variance slash standard deviation is always going to be a little bit larger because we're dividing by a smaller number for it. Okay, so that's it for that part. The next thing, kind of bringing in the standard deviation into like this mini other topic, which we'll actually be getting into in chapter 5, is the bell-shaped distribution. So imagine if we had a symmetric frequency histogram that looked something like this bell-shaped distribution right here. This is when we could use it. But we'll be getting into that in a little bit later. I just want to at least introduce it right now. So for the bell-shaped distribution, when a data set kind of resembles this shape, this bell shape, we have this certain rule called the empirical rule. So the empirical rule is going to say that when data sets are approximately symmetric and bell-shaped, we have about 68% of the data falls within one standard deviation from the mean, 95% of data falls within 2 standard deviations of the mean, and 99.7% of data falls within 3 standard deviations of the mean. So we can see on the graph up here, the mean's in the middle, which it always will be for these bell-shaped distributions, for these symmetric distributions. There's the mean. Could have used x bar as well, but we're just using mu. So the mean's in the middle. So if we go 1 standard deviation to the right, meaning we add 1 standard deviation to the mean, and then we subtract 1, we subtract a standard deviation, 68% of the data is going to fall with it between those two values, which means 34% on the one side and 34% on the other side. And then we're going to keep on going and adding another standard deviation. So we add 2 standard deviations from the mean, and then we subtract another 2. That means 95% of the data is going to fall within those 2 spots. And lastly, we're going to add another one. So add 3 standard deviations, subtract 3, 99.7% of data is going to fall between those. Technically, we could keep on going, but you can see that after 3 standard deviations from the mean, we have 99.7% of the data, which is almost all of it, so that's why we stop right there. So let's do one example with this. Okay, so suppose we choose a group of students and measure their heights. We find that the mean height of the students is 64.2 with a standard deviation of 2.9. Estimate the percentage of students whose heights are between 61.3 inches and 67.1 inches for this first one. So let's draw this. So we are given some information here. We're given the mean of the sample is 64.2. So I'm using X bar here because it's the mean of a sample. And the standard deviation, which is an S for the sample, is going to be 2.9. So I'm just leaving out the units for right now. But notice that the units are the same for our data and the standard deviation. Okay, so let's go down here and fill out this curve for us so we can see why it's useful. So we're told that X bar is 64.2. And the standard deviation was 2.9. So if we add 64.2 plus 2.9, that'll get us to 67.1. So that's the X bar plus the S. If we add another one, that's going to get us to 70. And if we add one more, that gets us to 72.9. Okay, and then if we go back to the mean here and we subtract 1 standard deviation, meaning we subtract 2.9, we get 61.3. Subtract 2.9 again, we get 58.4. and subtract 2.9 again, we get 55.5. So thanks to the empirical rule, we know that 68% of the data falls within those two values because they're one standard deviation away from the mean. We know that 95% of the data falls between those two values because they're two standard deviations away from the mean. And we know that 99.7% of the data falls between those two because they are three standard deviations away from the mean. And you can see the way the graph has it chopped up with the percentages. So it's the same concept, they just have it chopped up. For example, between one standard deviation and two standard deviations, 13.5% of the data falls between that. So same idea, they just have it chopped up a little differently on the graph. So we're going to use this to answer these questions now. So we want to know what percentage of people, of students, are approximately between 61.3 inches and 67.1. So 61.3 is right over here on the graph, one standard deviation to the left, and 67.1 is one standard deviation to the right. So that is one standard deviation to the left and the right. And we know that 68% of the data falls between one standard deviation. Next one, 58.4 and 64.2. So 58.4 is right over here. And what was the other one? 64.2 is the mean. So that's not perfectly between two standard deviations. So what I'm going to do is actually I'm going to add up those percentages. 34% plus 13.5% is going to be 47.5%. And then for the last one here, 61.3 and 70 inches. 61.3 is the one standard deviation to the left, and then 70 is two standard deviations to the right. So once again, I'm just going to add up the percentages between them. That's going to be 34% plus 34% plus 13.5%, which gives us 81.5%. So about 81.5% of the students are between 61.3 inches and 70 inches. So this height is something that is, if you made a frequency histogram for it, it's one of the things that is decently symmetric. So it's decently bell-shaped, meaning we can actually do these approximations here and be somewhat correct, assuming we have a decent sample. Okay, so we'll actually be coming back to this in Chapter 5, but at least wanted to mention it right now. Okay, so that's it for Chapter 2.4.